and welcome to the third edition of Solar 101. In the first edition, I took you on a tour of our solar system here at the house. In the second edition, I showed you some upgrades we made and how to wire a battery bank. Well, I got a lot of inquiries on how to wire the whole system, so that's what I plan on showing today. So let's head up to the roof and get started. Here up on the roof, we have 3 sets of panels, 2 on the patio roof, which you cannot see, 2 here on the shed roof, and 4 here on the main roof. Before we get into wiring the panels, you want to make sure they are at the best angle to the sun for your situation. In the northern hemisphere, like here in the United States, you want the panels facing south because that's where the sun is. In Texas, where we are located, 30 degrees from horizontal is the best angle for all year round. There are plenty of calculators online to help you find the best angle for your location. If you want more power during the summer when the sun is higher in the sky, you'll want the panels to lay flatter, closer to horizontal. And for more power in the winter, you'll want them angled up higher when the sun is lower in the sky. You can also make your panel angle adjustable to squeeze out more power throughout the year. But that means more expense and going up on the roof a few times a year. We felt the added benefit was too small to make our panels adjustable. If your roof happens to be close to the optimal angle, like my neighbor's as you see here, you can mount them on brackets close to the roof. You don't want them lying on the roof because you want the rainwater to pass under them and have airflow to keep the temperature down. The hotter the panels, the less efficient they are. Since our roof is not at the proper angle, we had to build these aluminum racks. To attach the aluminum racks to the roof, we used 4 to 6 inch lag bolts like you see here for each rack. We put roofing cement into the drilled hole, then inserted the lag bolt. We coated the head of the bolt with roofing cement to make sure there were no water leaks. These go all the way through the roof into a 2x6 rafter. Don't just attach them to the roofing plywood. They may not hold up in strong winds. We have had 70-mile-an-hour winds here since putting up our panels, and so we know they are secure. To secure the panels to the racks, we use 2 screws on top and 2 screws on bottom, like you see here. Now that they are secured, let's move on to wiring. As a safety precaution, only wire your solar panels when they are not producing power. This requires covering them with something dark during daylight hours. I use a large tarp. Make sure the tarp is secured. You don't want the wind blowing it off, exposing you to a possible shock. Another alternative is wiring them at night with the aid of a headlamp or flashlight. Be careful, as navigating up and down ladders and walking on roofs at night is trickier. Use a voltmeter to verify that the leads from the panels are not powered. I will use these 4 panels to explain wiring since they are wired in both series and parallel. Here on the underside of the panel are where the wires are located, both a positive and a negative. Since the 2 panels I'm connecting are wired in a series, that means the negative of one panel is connected to the positive of the other. If your panels happen to have the MC4 clips shown here, like ours did, you simply snap them together. If you have just wire without the clips, I will show you how to connect them in just a moment. Now that the negative and positive are connected, we are left with a negative and positive lead coming out. These panels are now wired in a series. If you remember from my previous videos, in series wiring, the voltage of the panel goes up and the amperage stays the same. Since these are 24 volt 8 amp panels each, they are now acting like a single panel at 48 volts 8 amps. These other 2 are also wired in a series, and the 2 sets of 2 panels each are then wired in parallel. In parallel wiring, the positive of each set is connected to the positive of the other and the negative to the negative. Normally you connect panels in parallel by use of a combiner box, which I will show you later in the video. Since we are installing a disconnect switch here on the roof, which I'll explain in a moment, we wired the panels in parallel to it. The positive and negative lead wires coming from our panel sets are not long enough to reach the disconnect switch, so we had to splice a longer wire to them. To do that, we removed the MC4 clips with wire cutters. You might want to check your paperwork, as some manufacturers void the panel's warranty if you remove the clips. With the clip removed, strip 1/2 to 3/4 inch of the plastic coating off the wire with the wire cutters, being careful not to cut into the actual wire. You can use a wire stripper like this fancy unit I have here to make a nice clean strip. With both positive ends stripped, screw on the appropriate size wire nut for the size wire you are using. Once secure, I tape the wire nut and the wires together to make sure they don't come loose and to help keep weather out. Tuck the wires underneath the panel somewhere to keep them out of the elements. We did the same for the negative side, as you can see here. An important safety note here before we move on. You want to make sure your panels are properly grounded, which provides a quick path to the ground to dissipate the excess voltage caused by a lightning strike. It helps protect your equipment and wiring and reduces the chance of a fire from the excess heat. And although we don't have them installed, you can use lightning arresters for extra surge protection. Just remember, a direct hit from a lightning strike is likely to destroy the fine circuitry of some solar equipment regardless of protective measures. We attached our bare copper grounding wire to the panels with pressure lug connectors seen here. The wire then runs with the rest of our wires to the disconnect box. We attached the wires with zip ties like this to the aluminum racks and spray painted the racks and wire jacket brown to help blend in with our roof. Here on the post of one of our racks is the disconnect. It's a switch that cuts the power coming down from the panels in case we have to work on equipment down the line. Let's take off the cover and see how the panels are wired into it. Once again, make sure no power is coming from the panels when making electrical connections. Coming up from the right side here are the two sets of positive and negative leads coming from our panels along with the two grounding wires. Both incoming ground wires are connected here to the ground bus bar. The thicker grounding wire here is the wire going out and down to the grounding rod. Since we are using the disconnect as our combiner box to wire the two sets of panels in parallel, you can see we have both positives, white wires, going to the positive terminal, and both negatives, black wires, going to the negative terminal. The two sets of panels are now wired in parallel. The two larger wires at the bottom of the disconnect switch are the positive and negative running down the roof to the shed. With the parallel connection complete, let's do the math to see how much power our array of panels are producing. Our two panels connected in a series produce 48 volts at 8 amps. The two sets we just connected in parallel produce 48 volts at 16 amps, because connecting in parallel raises the amperage but keeps the voltage the same. Okay, let's see how we can get the wires from the disconnect on the roof to the combiner box in the shed. You don't want wire running loosely along the roof and down the outside house wall where it will be exposed to weather and damage. In most places, it probably violates code. So we ran our wires through gray scheduled 40 PCV pipe, which is weather and UV resistant. You can pick it up at almost any hardware store. It's relatively easy to cut and glue together. If you're not sure what glue to use, just ask the clerk at the store. Again, if you don't feel comfortable working with PVC, you can always hire a professional to do the conduit work. There are various screw-on connectors, elbows, and flexible conduit pieces, so you can make just about any bend or connection you need. We used a screw-on connector with a rubber weather seal here to connect our disconnect. Then a flexible PVC conduit into our Schedule 40 pipe. It's hard to see, but this is our outgoing grounding wire. We ran it on the outside of the PVC pipe. We used twist ties at various spots along the PVC to secure it. This is done to prevent melting the positive and negative wires inside the pipe should a heavy surge or short circuit heat the grounding wire. Make sure to use a number 6 or heavier gauge when using an exposed grounding wire because it needs to be durable to withstand being outside. For the next step, instead of running the pipe around the roof edge, we opted for a cleaner look by drilling a hole in the roof and lining it up with the outside wall of the house below. Make sure to use plenty of roofing tar where the pipe meets the roof to prevent water leaks. All right, let's get down off the roof and see how we get our wires and piping into the shed. Okay, you can see the pipe coming off the roof through the hole we cut here. You'll notice we continued our twist tying the copper grounding wire to the pipe. This pipe here contains the wires from our two solar panels on the patio roof. Then both sets of wires meet here at this junction and continue on down the pipe. It's a bit hard to see, but here's where we join the grounding wires together. I'll explain all the other piping you see here later in the video. Our pipe with both sets of wires continues down the wall into the ground. We had to break through our cement walkway in order to put the PVC pipe containing the wires under it. It was more work than going overhead right from the house roof to the shed roof, but we wanted a cleaner look and no overhead wires. This is where the wires from the house and the patio solar panel arrays come up from the underground behind our shed. They continue on here to this junction box, where they meet up with the wires located in this pipe coming from the solar panels on the shed roof. You can see here and here where the grounding wires from all the panels are joined together and continue to our grounding rod below. If you need help installing a grounding rod, please use your favorite search engine and search how to install a grounding rod, or you may want to hire an electrician. Now, here where our junction box is located, we had to drill a 1-inch hole through the shed wall to get all the wires inside. So let's head on inside and see how it's all wired in the shed. From the wall, the wires from the 3 arrays come into this combiner box you see right here. I will take off the front panel so you can see how they're wired. The 3 white wires you see here are the positives coming from the arrays. Now they each go into a DC circuit breaker. Again, make sure you get DC circuit breakers because we're working with DC, not AC like your house. AC circuit breakers will not work in this situation. So the 3 wires go into the AC breakers, and then the breakers you can see are attached to a bus bar here. All this does is combine all 3 positives together, and then it connects to the red wire you see here going to the charge controller. Now the 3 negative wires are coming in and going to the bus bar you see down below here. This combines the 3 negative wires, and then we have the 1 black wire going to the charge controller. Well, you'll notice here you might see a little bit of red on that wire. That's because we didn't have a black wire. So we put tape on it to designate it as black, because you always want to keep your wiring straight. Red is positive, black is negative. Now we just have 1 wire each, a positive and a negative, so it makes it easier to wire to the charge controller. So let's take a look at that now. From the combiner, the wires go to our charge controller. So we have the negative and positive and the ground going to our charge controller. I won't explain how a charge controller works. You can see one of my previous videos for that. I'm just showing you how it's wired. So they go inside the charge controllers before it goes to the battery, because this is going to control the state of charge to our batteries. So let me go ahead and open this up and I can show you how it's wired. I'm going to use arrows on the screen to show it to you because there is power going through the system and I don't want to be touching the wires. So you'll see we have the negative and positive coming from the combiner box going to the input here on the charge controller. Then we have a negative and positive from the charge controller going out to the batteries. On the positive leg going to the batteries, we have a 63 amp breaker. This allows us to cut the power to the charge controller by turning off this breaker and the solar panel breakers if we need to work on the controller. You can see the red positive wires here, one coming from the charge controller going to the top of the breaker and one coming out of the bottom and going to the batteries. This DC breaker is polarized, so the side with the greatest power potential, our battery bank, needs to connect to the plus sign on the breaker. The breaker must be wired correctly for it to function as designed. The blue wire here, that's a temperature gauge. It's attached to one of the batteries. It helps the charge controller to charge the batteries correctly if it knows what the temperature is. This green wire here that you see in front, that goes to our router, which connects to our Wi-Fi in the house. And that's just so I can monitor the charge controller from my computer. Now you'll notice back here, these are all the grounding wires. One comes from the combiner box, one's coming from our breaker here on the right hand side, and then one's coming from the classic itself, and then the other one's going outside to attach to our ground out there. So that's how the charge controller is wired. So now let's go to the next step and see how the batteries are wired. This box here contains our batteries. It's mostly to protect our batteries from damage and weather. It's not sealed, which allows our flooded lead acid batteries to vent the explosive hydrogen gas they give off safely into the air. Although more expensive, use sealed batteries if they are going to be inside your shed or where they can't be vented. To get more information on battery maintenance, selection, and safety, see my other video, SolarPowerE 2nd Edition, Upgrades and Battery Bank Wiring. We drilled 2 holes in our shed to accommodate the in and outgoing wires. The black wire here is the negative coming from the charge controller and the red is our positive.
The smaller blue wire is the battery temperature sensor. I'll explain the two larger black wires a little later. Our battery bank consists of two sets of 4 batteries wired in a series. The two banks are then wired in parallel. It may be hard to follow as I explain the wiring because our batteries are not all oriented in the same position. We position them for ease of wiring. Our inverter is 24 volts, so our battery bank needs to be wired to match. We are using Trojan T105-RE 6-volt 225 amp hour deep cycle batteries. These are made specifically for solar applications and have very thick plates inside. Golf cart batteries are okay, but do not use auto batteries. They have thinner plates inside and will not hold up in solar applications. To get 24 volts for our inverter, we wired 4 batteries in a series, connecting the positive of one to the negative of another. We did this 3 times, as you can see here. Wiring this way makes the volts go up and the amp hours stay the same. So we now have 6 volts times 4 batteries for 24 volts, 225 amp hours. We wired another 4 batteries the same way. Then we connected the 2 sets of 4 together in parallel by connecting the positive lead of one set here to the positive lead of the other set located here. Then we connected the negative here to the negative of the other set here.
Since our battery configuration makes it confusing, let's take a look at a diagram of parallel wiring with all the batteries oriented in the same direction.
Wiring in parallel, the amp hours go up and the volts stay the same. So our two 24 volt 225 amp hour banks become a 24 volt 450 amp hour bank. This gives us more battery capacity to run things, but keeps our volts the same as the inverter, 24. Notice that we used a very heavy gauge wire, 2 over and 4 over, for our battery bank. The wires can be expensive, but you don't want to skimp in this area. In our setup, they may need to carry up to 166 amps, so a 2 over is the minimum required. Here is where the charge controller connects to the positive of the battery bank. Clear over on the other side is where the negative connects. You want them on the batteries at each end so that all the batteries are charged as evenly as possible. You may notice that these wires are considerably thinner than the battery wires. That's because they will carry less than 60 amps, the most our panels can produce, in our setup, which only requires a 6-gauge wire. To connect the batteries to the inverter, we used 2 3-foot 4 over gauge wires. A positive connected here on one end and a negative connected on the opposite end to the negative terminal. Again, you want them connected on the end batteries so the bank will be depleted in a uniform manner. Here you can see the large wires going from our battery box through the holes drilled in the shed wall. Now let's go inside the shed to see how the wires connect to the inverter.
The positive and the negative from the battery come into our inverter here. Now it's a little difficult to see, but I'm going to do my best to show you the wiring. The positive runs through a 250 amp circuit breaker on the positive leg coming from the batteries to the inverter. Now what this does is it prevents a catastrophic short circuit, or we can turn it off to work on the inverter. Now someone may say, why 250 amps? Well, because a lot of times when you start equipment, it takes a lot of amps just to get going, and if it was any smaller, it would constantly be tripping. Now I would show you how it's wired, but because it's in the wall, it's very difficult to look at. But it kind of works the same way. From the battery, it goes through the bottom of the circuit breaker, and then the red positive from the circuit breaker comes out and goes to the inverter. You can see the positive and negative coming from the batteries into the inverter. And then down below there, it's hard to see, but those are where the wires coming out of the inverter and go into our AC panel here in the shed. And there's also another wire in there, you can barely see it right here. That goes to our control panel. And then down here on the very right, again tough to see, there's a copper wire, and that's our grounding wire going outside to the ground. Okay, that one gray wire coming from our inverter goes to our control panel, which is right here. It just lets us know what's going on with the inverter. Alright, now let's see where the AC comes out. Okay, this is our AC panel. The power comes from the inverter to this panel. I have the door open so you can see the circuit breakers. I'm going to go ahead and take off the panel so you can see the wiring behind it. Okay, so here's our AC setup with the panel removed. It's pretty much wired like your home is. The two black wires you see here are the hot wires coming from the inverter, and they attach to these bus bars. And then our circuit breakers are attached to the bus bars. Now remember, these are AC breakers because we're working with AC now. From the breakers, you have the black wires going out to the various outlets throughout the shed and the house. Now, the neutral wires, the white wires, and the grounding wires are all attached to these side bus bars. They go to the various outlets also. The only exception here is the upper left AC breaker. It's a GFCI, so it's wired a bit different. It's used to prevent electrical shock wherever water may be present, like in a kitchen, bathroom, or outdoor outlets. The black, hot wire is wired the same as a normal breaker, but the white, neutral wire here comes directly out of the breaker and runs to the protected outlets. There's another white neutral, which is coiled here, which runs from the breaker to the neutral bus bar. You must wire the GFCI correctly in order for it to work properly. Please follow the instructions that come with the GFCI, making sure to follow all your local building codes as well. You can always hire an electrician if need be. So how do we put our solar generated AC power to use? These two breakers go to various outlets around our shed to run lights and equipment. These two go to the house. The wires come out of the shed here and run through PVC all the way to this cutoff switch. This allows us to cut the solar generated AC power to the house. This branch here goes to 2 outlets in 2 different bedrooms. The other branch goes to 4 outlets, 2 of which are in 2 different bedrooms and 2 that go to different locations and have refrigerators plugged into them. In the bedrooms, we use the solar generated power to run various TVs, lamps, phone chargers, DVD players, and the like. When we get those rare 2 or more cloudy days in a row, we sometimes have to switch one fridge from the solar generated AC and plug it into a regular house outlet to keep the batteries from being depleted. Okay, before we end the video, let's take a quick look at one of the solar outlets in the house. Okay, so here's where we use the solar power in the house. The outlet on the right is power coming from the power company. The outlet on the left is our solar power. That's taking power from the batteries, which our solar panels replenish every day. Well, that's it for solar power. I'm DrewShock saying so long.